Welcome to the first video of our series on different kinds of coordinate systems. So first we'll look at the one that we use most, Cartesian coordinates, or some people know them as rectangular coordinates. It's the basic, you draw your x-y axis, so x, y, and then you plot your points and stuff, you draw your curves and such. It's that coordinate system. So it was originally devised by René Descartes, French mathematician. But let's look at what constitutes a Cartesian coordinate system. So the first thing we need, number one, is an origin to know where we begin. So let's just start drawing our picture here. So here's our origin. And then the second thing we need is axes. So we can put two axes, we can put three axes. So let's put two. So the standard ones we usually use are the x and y, so they go straight up and down and horizontal. But let's use some unconventional ones. So let's use these just for fun, and the axes will be perpendicular to each other. And then the third thing we need is a positive and negative relative orientation for the axes. So I'm going to call this positive on this axis, and this is going to be negative on this axis. This, for fun, will be negative, and this will be positive. So I have defined those. And the last thing we need, number 4, is unit vectors. So we need to know how long a unit is for each thing. So in each axis direction, I have to define a unit vector. So here's my first unit vector for this way, and I'll call that I'll call it A, my A unit vector. And then here I'll define in the positive direction a unit vector B. So that's my 2 unit vectors. So now that I have all 4 parts, we have a coordinate system. Now you notice that here B is going in the positive direction for this axis, but A is going in the negative direction. So in the positive direction, we would have negative A vector. So that's how that's defined. So now with all 4 of these parts, we have ourselves a Cartesian coordinate system because we have everything met. And I can define any point in space using these. So for example, if I just define this point in space, P, then that P is defined because I know how far away it is from each axis because of my unit vectors. I just add up unit vectors like that. And I know relatively where it is for the axes, and I have an origin which to measure it from. So that's how that works. And the most standard axes we use almost all the time when dealing with Cartesian coordinates is x, y, z. So I just thought I'd provide a drawing of that. So usually in these coordinates, this is x, this is our y, and this is our z. X is coming out at you. So if you imagine this line is coming out towards us. So that's how those are defined. And the last thing we can do is talk about a little bit of calculus of these things. If we have let's go back to 2 dimensions for just a sec. If we have our standard xy axis coordinate system, then we can define an infinitesimally small length. So this has length, but I'm going to pretend it's infinitesimally small, as dx or dy if we have in this direction. So infinitesimally small lengths. And if we take 2 of those lengths and put them together, so let's say I take these 2 lengths and I put them together into an infinitesimally small area, I have dA equals dx dy, or dy dx. And now if we expand our analysis to 3 dimensions, and I draw my axes again, let me label them. So x, y, z. If I expand it to 3 dimensions, then I'm going to have an infinitesimally small volume if I have in the z direction, in the x direction, and in the y direction. So it's going to look something like this, where, let me draw this a little bigger. So it's going to look like this, where this is dz, this is going to be our dy, and this is our dx. So that means that dv equals dz dy dx. And keep these things in mind. We'll be using these for multivariable calculus problems and topics a little bit later.